we added into our normal data bank, in addition to the ROB, also the MOB, and we said the main reason that we're adding this back is we want both to hold the intermediate values before writing to the permanent state, right? And we said the main reason we're doing this, which is what we call is the basics of the B6 architecture, is we want to maintain precise state, right? Because we had the problem in Tomasul or in scoreboarding, is that I'm combining two things together, writing permanently into the register file or the memory, as well as broadcasting the value to everyone else, right? We said the problem with this is if I'm doing out order execution, if I'm reordering stuff, and then at one point if I have an interrupt, for example, or we call it generally an exception, right? In that case, or well, a branch speculation as well, and you need to flush. You don't know what to flush because some instructions have already finished executing, writing permanently into the register files, and hence to the register file or to the memory, and hence you cannot really retrieve what they have done, right? So you cannot really say, okay, I'm going to just roll them out and try to repeat from the beginning. This cannot happen because you have already rolled, right? And we said the key observation here is that as far as I didn't write to any permanent state, which is again my register file and the memory, then I'm fine because everything is executing on the fly, more or less a combination of logic and the execution unit. If I want to throw everything away and then re-execute the instruction from the beginning, I'm fine, right? How to do this? Well, simply by maintaining the data once the execution is done into the ROB or the MOB and only write to the register file or to the memory on what we call the retired state, right? So we split the write back into what we call complete and then retire. And retire is actually when the instruction is completely removed from the ROB and from the MOB as well. While the complete means the execution is done, but I'm waiting to write back permanently into the data based on what? Like if an instruction is completing, what is preventing it from being retired? What is the transition from here to here? Yeah? Yeah, correct. Yeah, thank you. Which is in a more, I would say, concrete terminology, we are retiring instructions in order, right? So we said for out order execution, we are in fact fetching instructions in order for the ROB. We're not taking them out, but rather reading from the ROB, executing them out of order based on which instruction is ready, and then retire them out of the ROB in order as well. So you insert in order, you pop out in order, but you execute out of order, right? Make sense? So that's the key basically of modern out order execution. This is really what's happening in almost any out order machine right now. Good. Aside from the low-level implementation details. Then we said, okay, Tomasul plus ROB is simply our B6 architecture. We are separating the ROB and the reservation stations. Again, because I want the ROB to maintain the intermediate result, while the reservation station, which includes the function unit as well as the register values, right? Written there. And this is B6. Well, this is mainly bake and prove. It also exists in some of the IBM and IND architectures, as we'll see later on. Assume that we want to rerun the same example we had before, which we had one ALU, one load, one store, and two floating points. Everyone is taking one cycle, except the floating point is taking 3 cycles. And let's repeat the example we had about the array vector multiplication in the B6 architecture and see what happens, right? But similarly, well, for scoreboarding and Tomasul, also for B6, before we go there, let's see really how the architecture looks like, right? Someone can look here and say, well, this is pretty much Tomasul, right? It's really what we had. We had a register file, and then we have function units that also had their own. This is the reservation station, including function units, your local version of the data, as well as your tags, right? And then you have the register status and the register file. The only thing we added is this ROB block, right? That's really the new part where I allow the ROB to also hold register values, right? This is the key part that allows me to only write from the ROB, like these arrows that you see now, to write from the ROB to the register file only on retire. Now you see also that the common data bus, when a function unit is done execution, the common data bus does not write to the register file, right? In Tomasul, we had this bus here going to these values, but also going to the register file, right? Right now, we have broken it into two. The common data bus takes the value from the function unit and then do the execution right to the ROB, and the ROB is retiring to the register file only in order. Good. So this part is the key difference here. We broke down the common data bus path to the register file to write instead to the ROB, and then the ROB is retiring in order. Make sense? Okay, what data structures? Everything is exactly the same, except that now, right now, I have an ROB. Well, that also holds the data as if it's a register file. It has a head and tail because I want to keep the order of instructions. And it also has the output register value, right? This is the key part that is different than what we discussed very early at the beginning of out order execution for ROB, that you also hold register value results. Previously, at the very beginning, before we talk about scoreboarding with Tomasulu, we had the ROB on our data path, but we used it only to schedule instructions, right? Right now, we're also allowing the ROB to hold the data output of this instruction, again, to decouple the result of the execution of this instruction from writing to the register file. And then during dispatch stage, the only thing that has changed is right now I'm also checking whether I have a space in the ROB or not, right? And the space means like also space to write the data, not only a space to insert the instruction. And then if you have all the resources needed, you simply also set the RSC, the register station tag, sorry, the reservation station tag to the ROB number. Because right now ROB is the one that is really maintaining the instruction data. And you also, instead of setting the register status to the reservation status, reservation station number, you set it to ROB number, right? So this is what you do differently in your example. Previously in Tomasulu, we used the reservation station number as my tag, that this function unit is the one that's going to write to this register. But right now, register file doesn't care about reservation station because we have broken that path. It cares about from where in the ROB my result will come. So why we replace the reservation station with the ROB number. Good. And then the issue is just exactly the same. If there is a read after write dependency, you stall, otherwise you execute. During execution, just exactly the same as well. Now, in the last stage, instead of write back, we split it into two, complete and retire. With a complete, this is where you take the result from the function unit and write it to the ROB. So you check whether your common data bus is available. If it's not available, that's a structure hazard you have to stall. Otherwise, you broadcast the value of the tag. We have done this in the past, right? Broadcasting with the common data bus. But this broadcasting is going to end. This destination is the ROBs, right? In the entry that is indicated by the reservation station tag. And then you mark the ROB entry as complete. Because once you mark entries as complete, when you try to retire instructions, you only retire the complete ones in order. And then you mark the register status entry to be ready in ROB. Why I'm doing this step? Why I want to say, well, this register value, this result is ready in ROB right now. What do you think? Yeah.
If another instruction wants to access that value, it'll check the ROB.
Exactly, thank you. So basically, again, this is the bypassing forwarding thing, right? I don't have to wait for writing into the register file, because even right now, writing to the register file does not happen immediately. It just happens maybe after few instructions because of the in-order enforcement I've done. So I can take the result from the ROB, right? So that's the bypassing logic. Good. So this is for the complete stage. For the retire stage, this is simply when the instruction will be removed completely from the ROB. Now, I need to check the head because I'm retiring them in order. So the ROB head is complete. Well, if the head is not complete, I cannot really retire anyone else, even if it's complete, because I'm retiring in order, so I have to stall. If the head is complete, then I see, well, if there is any exception pending, I handle those exceptions as we see later on in the example. And then if there is no exception, or I have already handled the exceptions, I write the ROB into the register file or to the memory if I want, basically from the mod to the memory. It depends on whether it's store or any other instruction. And then once I'm done retiring by writing permanently to the state, register file or to the memory, I free the ROB entry or the MOV entry, and then I move to the next instruction. Good? In reality, this is the closest implementation to what is in Maxim, right? So if you go back to, well, the if statements in the out of order scheduler, and you see when Maxim retires instructions, for example, or check for a ready instruction. For the retiring, you'll see that it's only checking the head. If the head is completed, it basically write to the register file or to the memory, otherwise it does not do it, right? So this is, well, because we are short in time, I didn't do this, but ideally, in fact, I can really give you here the code snippet that exactly implements that logic, right, in Maxim. And I'm hoping in lab 2 you have already given it some look. Okay, so we have discussed what happens during stages. This is just simply a visual view of those stages. During the dispatch, I need to allocate my resources. So I allocate the reservation station, and then I'm also writing the ROB number that I'm going to write the result to. Set registers entry to ROB number and ready in ROB to 0 because I'm going to write into it. For the dispatch, well, I need to see if all my register values are ready in the register file. I'm going to read them. If they are not ready from the register file, what do? Well, they might be ready now in the ROB, right? Because I also have the ROB values. This is the example of this. This register, for example, R2 here, which is value 2, is ready in ROB. So I just read it from the ROB directly, right, into my local reservation station. If it's not ready at all, then I have to wait and keep monitor the common data bus, right? This is a typical example of a read after write dependency. You stall and every cycle monitor the common data bus to see if the value is broadcasted. Yeah, so in the complete stage, we bypass the execution because just you execute with the function unit. In the complete stage, you have the result ready at the end of the execution. You broadcast it in the common data bus if it's available, and you write it to the ROB in the place where it was marked here by the ROB entry, right? So here you already had a tag where you're going to write your result once it's done, and this is basically ROB entry, which is you're going to write into it here, right? And then finally for retire, well, if this is your top instruction or your hidden instruction and it's marked as complete, you take the value from the ROB, write it to the register file, then you need to clear your tags basically that, well, this one is already done right now. Make sense? Again, a lot of well, animation theory stuff, it will be clear through the same example we had before, right? This is the same code snippet we had for the array or the vector scalar multiplication, and let's see what happens during execution. One thing you observe that I've done differently here is I named this thing ROB plus MOB, and I'm also adding R and V. R is the actual register, and V is the value itself. And then we will see that, well, these structures are exactly the same, but the difference is that I will insert the tags to be related to the ROB entry, not related to the reservation station. So during cycle 0, cycle 1, what happens is that this instruction want to be dispatched. Well, the reservation station is empty, the ROB is empty, and everything is basically available, so I can reallocate it. What I would do is I would say my destination register is F0, and then this F0 is going to get ROB entry 1 because this is the first entry in the ROB, right? You can think of it as, in fact, a FIFO, right? This is taking the top of the FIFO, this first entry, this is why it's 1 here. What does this mean? It means that any instruction afterwards that is looking forward to result F0, for example, here the multiplication, will have to read ROB entry 1, which is simply this value here, if it's available, right? And then the same thing in the reservation station. I say, well, is my sources ready? R1 is ready, definitely. So this is why I'm reading it directly from the register file. I don't have in a load, you don't have another register, you don't have a second operand, but you have a destination. Your destination is going to be marked as ROB entry 1. Why I'm doing this here? What do you think? Why I need to keep the tag of the destination I'm going to write to in the reservation station? Because everything we do here is for a reason, right? I mean, for an intuitive reason, yeah. Well, yeah. The point is that if I don't want anyone else to write into it, this will not have it even if I not write into ROB1 here because it's already reserved in the ROB, so right? But I write it here for another reason. Who is going to write to the ROB? What do you think? Who is going to write the result into the ROB?
The function unit.
The function unit, the reservation station. But where does it write? Yeah, that's when it writes, right? When it's complete. But where does it write? ROB is in fact like a queue, right? Or a buffer or a lookup table. So where to write? In our example, it's ROB1 for the load, right? How do I know this if I don't really store it as a reservation station, right? So the reservation station needs to keep track of where in the ROB, because you index this ROB, this one, with simply like similar to the register file with an address, right? Or an index or anything, right? So you need to know at which entry in the ROB you need to write. And the one that's going to write is the reservation station. So there is no way for me to know except that I need to record where I need to write my destination, right? That's why we keep it here. Good. So I'm done with cycle 1, dispatching the load. Cycle 2, the load is moving forward into the yeah, please. Oh, this one? I will come into it. Yeah. Thank you. Good. Then, so the second one is, well, in cycle 2, the load is in fact issued, right? This is in cycle 2 here, you issue it, while the multiplication can be dispatched. When I'm dispatching the multiplication, I need to check whether the resources are available. I have a floating point reservation station available. I have an entry in my ROB, so simply I can allocate it. So I make the reservation station busy. Right now, what are my sources? F0 and F2. Well, F2 is available from the register file. This is why I get it like register file F2. For F0, which is source 1, then, well, this one is not really available because there is a dependency. How did I know? I went into the register status and I found F0 was marked with ROB1. I copy this tag into my own tag 1, right? Pretty much similar to what we have done for Tomasuru, but using reservation station numbers instead of ROB numbers. And then what about my destination? My destination is F4. So I have to reserve F4 for myself. I'm occupying ROB number, like basically entry 2. So I'm saying ROB entry 2, and I'm going to write here in the reservation station into ROB entry 2. Good. And then in cycle 3, what I'm doing is, well, let's start by the load. I already issued it, so I can start executing it. So I'm executing the load of cycle 3. And the multiplication, it cannot be in fact issued. Why I cannot issue the multiplication? It's a read-write dependency, right? Well, because you are waiting for F4 to be written. F4 is currently not ready in the ROB, not broadcasted in the common data bus, you have to wait. And I can simply issue the store. Issuing the store, I allocate the store unit, and then look into my sources. I need R1. Is R1 ready? Yes. So you basically take it from, is R1 ready? Yeah, no one is going to write into R1. So in that case, it's register R1. And I need also F4, but F4 is going to be written by the multiplication. Going to the register status, F4 is ROB entry 2. So why I mark it as ROB entry 2 here. Well, do I have a destination for the store? Yes, memory. Because remember, the store is the special instruction that is handled by the MOB side of things. Here we combined ROB and MOB as one entry, right? Which is also one valid implementation, not too far from one of the existing implementations out of order. And the store has taken entry 3. This is why my value that I'm going to eventually write to the memory will be held into entry 3 in the ROB. So I mark it as ROB 3. Good. Makes sense? But observe that the store didn't in fact tag anything as destination in the register file, because I don't write to the register file. It's mainly my memory, right? And then cycle 4, the load is complete because I'm done loading. It's not, well, do I retire it or not? But the load can retire as well, but that's a different story. It's complete, which means I have already brought the data from the memory, which means also the multiplication can be issued right now, right? What about the store? The store is still, in fact, waiting for the F4 value, so we still have to wait. But I can issue the ad. If I issue the ad, I look again to my, well, first of all, I allocate the reservation station. This is the ALU. I have R1 as a source and then an immediate value. So I take register R1, and then V2 will be the immediate value, so I don't have to worry about it. And then my destination is going to be R1. In that case, I have to, this is my entry 4, so I have to tag R1 to be ROB4, and then I write it here into my destination. Good. So for this question related to the head and the tail, so if you see at the beginning here, I'm tracking. Remember that we said the ROB need to maintain the head and the tail because it needs to know which instruction is the top and then simply the size of your ROB. At the beginning, because you only have one entry, it's both the head and the tail. But then by executing more instructions, it moves, well, my tail here is multiplication, and then it moves to the store and then to the add, right? So that means right now, well, we have this visibility because we are doing a paper and pen analysis, but in reality, in the hardware, in the ROB, those are the instructions existing in my ROB, right? Makes sense? These ones didn't come yet. Okay. Then at cycle 5, in reality, I have retired the load, right? Because it was complete at 4, and then this is the top or the head of my ROB, so I can retire it. How do I retire it? Simply clear the entry from the ROB and move your head, right? So the head right now moves to the second instruction. So at cycle 5, load is completely out of my state in the hardware, completely done, written to the register file, and multiplication is my top of the ROB. Make sense? Also at cycle 5, I started executing the multiplication. This one is still waiting for the multiplication. For the addition, I issue it because R1 is ready, available, so I issue it. And then I'm also dispatching the load instruction. The load instruction, again, it's going to write into F0. It needs R1, but R1, in fact, is going to be written by the add instruction here. So you see right now, when I reallocate this reservation station, I no longer is able to write register R1 is ready, but instead it has to wait for ROB entry 4, which is simply allocated for R1 here. It's going to be written by the, and then as a load, I'm going to write into F0, so I'm reserving back F0. My entry in the ROB is 5, so I'm marking it as 5 right now. And I'm going to write the destination here to be 5 for the load. Questions so far? More or less what we do is exactly the same, except that we are also maintaining what is happening inside the ROB/MOB, right? It's head and tail, which one is retiring versus not, and then keep track of the ROB number, where I can find the result or where I should write the result. Make sense? Good. And then we'll continue doing that. So I believe if I just go through the whole example, just be exactly the same thing. So maybe one example, let's make something that might be meaningful. Here, for example, when this ad is complete at cycle 7, it also broadcasts the stuff in the common data bus. You see here that the common data bus has the R1. In that case, also the load can move forward and start being issued because it finds the data ready on the common data bus, right? Now, this is an example of ensuring the retiring in order. You see that the add is done at 7. While, for example, something like the multiplication will only finish at 8. Why? Maybe I'll just go one cycle back. This one is completed at 7, which means at 8 it should be able to retire, right? But then 2 instructions didn't retire yet. So my add is not the head of the ROB. So I cannot retire it. For that reason, I will keep the add into my ROB, store the retiring stage until the order comes in, which means until I retire first the multiplication and then the store. This did not happen into Masulu, right? Into Masulu, we wrote back this instruction at 7, we got it done, we forget about it, right? But right now, I don't write the result in the register file. I keep it in the ROB until everyone else is done and then write to the register file. So this is the enforcement of basically the in order retiring of the B6 architecture. Good. Questions? Yep. Which one?
The V column and ROB.
That's the actual value, because remember in the ROB and the MOB, we want to maintain the value of the result because we read it from there, right? And for example, let's say here,
Is there a column that MOB?
which one?
Sorry, continue.
So let's make an example of something that retired. Cycle 5, for example, for the load, it's completed at 4, and then which means in reality, well, one cycle back, this one here, this value here is empty. I didn't write anything yet, right? But I know once the load gets the data from the memory at the complete stage, it's going to update this entry in the ROB with the actual value of the register F0, because this is what I'm loading into, right? So at cycle 4, I write F0 value here. I don't write it into the register file.
That's the ROB.
That's the, yeah, this is the whole ROB, right? This is in reality what we call ROB plus MOB. But I'm using it also to track register stuff, right? This is why it might be a little bit complicated. So here I'm tracking all the stages that you are following, but in reality I'm using this architecture to be the ROB that holds the instruction, its destination register, and the value of the register. Right? Make sense? Did this answer your question? So okay, so let's say I completed and I got the value from the memory. I write it here. I don't write it to the register file. At cycle 5, I'm retiring the load. What does it mean to be retiring the load? It means take this value out of here from the ROB, go and write it to the register file, and clear the register status tag that you have. That's really what you do, right? Does make sense?
What other instruction is that? Is it add as well?
Every single instruction that is going to write to the register file, or in fact even the store, is going to write to the memory. It does not write to the permanent state location, whether it's memory, the register file, but write to the ROB. And then this is at complete stage. And only at the retire stage, I copy the value from the MOB or the ROB and write it to either to the register file or to the memory, and then remove the instruction from the ROB. Right? This is the animations we had in the earlier slides, right? Okay, so for example, for the add, when I come here, we said at 7, the add is complete. It writes the result into R1 here. This thing means a value, right? The actual result of the addition. Then it maintains here until it retires. But the good thing about the add is that it cannot retire at 8 because I forced the order. So I keep the value here. I don't want to lose the value of the add, right? Until I'm retiring it. So I keep it here. So this is why it's not removed, similar to the load. And it's here until, in fact, I'm able to retire that, as we'll see later on, right? So if I look into what happens with the add, at 8, I'm retiring the I'm completing the multiplication. At 9, I'm retiring the multiplication, so I'm moving the head into the store. At 10, I'm completing the store. 11, I'm retiring the store. I'm coming to the add. Given that the add is head right now, the value is ready at the ROB. I can really retire it because the add was marked as complete. So in that case, at cycle 11, well, it's not here, but in reality, what happens at 11 is I'm just retiring the add instruction. Good. Yeah.
Is the R column, is that basically the dispatch stage? Or?
This one?
Yeah.
Yeah, this is simply your destination register. Like what we said is we are tracking into the ROB is because put in mind that also the ROB is the one that is going to write exactly the same reasoning why I need to maintain ROB 7 here, which is the index inside the ROB. In the retire stage, the ROB is the hardware that is going to write the value into the register file. Where to write? I need the address of the register, right? So this is the address of the register, and this is the value that I'm going to write to the register. This is what's called R and V. R is the address, which is a 5-bit of the register file address, and this is the actual values I'm going to write there. Questions? Good. So how do we maintain precise state? So we said the whole reason about having this ROB and maintaining the intermediate value there is to maintain precise state. So let's say I have, well, this is just theory. So let's say I have something like an exception here. Let's say at cycle 11, for example, assume I'm trying to retire this store, I got an interrupt, right? Before retiring my store instruction. So at cycle between 10 and 11, I'm simply before retiring the store at 11, I'm receiving an interrupt. What do I do? Based on what we discussed earlier, anything that has already retired, it's completely done. You don't need to worry about it. Anything that is currently in flight, which means it did not retire, even if it is complete, you basically zero it out, right? So you flush completely the ROB as if nothing happened, which means the load and the multiplication are done already, but even the store, even if you have the result ready, you're not going to write it. So when you are coming back from your exception, which instruction you are going to start from? In that case, yeah, it's the store, right? Why that's safe to do so? Because, for example, even if the add is also complete, I did not write the result yet into the register file. So it's safe to start from here and, well, basically execute everything from beginning. Good. So again, what we do in case of exception is you say, I stop here, everything that I did not retire. How do I know if I didn't retire anything? Because it still has an entry in the ROB. Anything that is in flight, which means it has a status in the ROB, flush completely. What retired is already retired, and then come from your head of the ROB. This is come back when you come back from the exception. You basically start from the head of your ROB. Yeah.
So, are we starting from the head, or are we starting from one point? So we're starting on the store. And
well, yeah, that's a good question. So in reality, what we're saying here is, well, I copied this from the previous slide, which means at cycle 11, I was able to retire the store. But what I'm saying that the exception happens before you retire the store, which means in fact this head has not been moved, right? You start from the head. Yeah. Make sense? So right now it's very easy to handle at any point, at any cycle when the exception happens. The logic is pretty much easy. Anything in ROB, you flush, you start from your head of ROB. Anything that retired, just retire. So I'm fine. Good. Yeah, so basically this is faulting out everything, and then when you come back, you start from the store. Make sense? Questions? Okay, good. So what we have done so far is we took the basic of out-of-order execution, and then we had one example implementation, which is scoreboarding. That was a bit limited. There is no bypassing. It's a centralized architecture, so it's very low performance. It does not handle write after write or write after read. And then we upgraded it a little bit into Tomasulo's algorithm, and we said some of the features in Tomasulo is currently still implemented, including register renaming by handling write after write, write after read. And you also do bypassing by the common data bus. But we said the problem with this is, how do I handle the problem that appeared because of the out-of-order execution? A problem that I did not have, I did not have in the in order, which is if an interrupt happens or an exception happens, where do I come back? How do I maintain correct execution, which is what we call precise state? We said, well, the way to do this is you need to split into your write back stage into two. Completion is one thing, but retiring by writing permanently the state into the register file or the memory is another thing. And we call this the B6 architecture, which is an upgrade of the Tomasulo algorithm to handle the precise state, right? This is basically the 1 minute summary of what we had in the past 4 lectures. Good. So what about the performance of B6 compared? We already discussed the performance of Tomasulo versus scoreboarding. It's clearly Tomasulo is better in terms of performance. What about B6 compared to Tomasulo? Well, generally, because it didn't change much in terms of architecting the actual decisions, other than maintaining the precise state, it's generally the same performance. In terms of organization, B6 in fact was a very popular design for almost a decade. And while it was adopted in more or less in Pentium Pro, PowerPC for IBM, AMD K6 architecture, which is also another old x86 architecture from AMD. So it was adopted by many of the machines during ages. If you observe, we in fact keep copying values throughout our architecture a lot. Like for example, I first copy the values either from the register file to my reservation stations or from the ROB to my reservation stations before I start, right? And we said the need for this in Tomasulo is register renaming, right? So we copy the values here. That's the first copy. Then when the result is done, I copy it into the ROB. And then when I want to retire, I copy it from the ROB to the register file, right? So at the very least, you do 3 copies of data throughout your architecture for one instruction to execute. This is too much data copy. Why data copy is a problem? Because, well, you require out of wiring, you require power consumption, which is huge, which is one of the main reasons, and you also limit your performance. You cannot really scale as much, right? You need too many muxes, buses, and then an additional observation is that either ROB or reservation stations, in fact, I mix the value with the tag. So I maintain not only the tag, but also the actual data values, right? When I go back to this example here, I was explaining in ROB, I'm maintaining my tag, but also the value I want to write. Also in the reservation station, I'm maintaining the tags, but also the values I want to write or read from, right? This is another observation that might be limiting the performance and the scalability of the B6 architecture. Some solutions simply is to say, okay, to minimize the copying as well as to split the control from the actual values, you simply decouple those tags, this control from the actual data maintained, right? And how do I do this? Instead of splitting my data everywhere, an observation could be, well, why I'm really copying the values into reservation station is to do register renaming. But if I'm paying the cost of this area anyway to replicate my registers, why I don't create a very big register file? So instead of having these 2 values here, instead of having them here, why I don't mix them with the register file, and then this gives me 2 additional registers. And then every single 2 that are in the reservation stations, if I append them to the register file, I simply can rename within the register file, right? So you basically maintain a very big register file where the data is only there, right? And because the register file is very big, then you are sure that every time you need something at the architecture or the assembly, there is a place for it in the register file. So simply you maintain a condition that the number of physical registers must be larger than the number of architecture registers. Those architecture registers or modeling registers are the ones that are generated by the assembly, the ones that are defined in the ISA document of the ISA. For example, 32 registers, right? If my physical registers are larger than 32, then I will never have the problem of write after write because I can always basically move them around, right? Makes sense? So instead of copying to another place, expand the size of a register file, and hence you do the renaming in place, basically, right? So you maintain one big physical register file, and then the ROB and the reservation station no longer keep data; they only keep the control and the tags, and then keep the physical register file close to the reservation stations such that you don't do a lot of data transfer, right? Good. Well, there is no architecture register file because I don't have 2 separate entities. There is no register file and reservation station values. There is only one physical register file where the number of physical registers, as we said, is already larger than the architecture registers. And then you do the mapping. And then the mapping you will always have a mapping. So the mapping cannot be 0 because again, there is no real architecture register file. It's only one big register file that can hold everything. And by doing this, you are simply again removing the write after write and write after read hazards, but in a more scalable way. Your free list that you maintain, it's also still, remember when we had the register naming slides, we maintain the free list of the registers that are not currently used. Just exactly the same thing. You also keep a track of unallocated physical registers in your register file. Once the ROB is returning an instruction, well, it will also, in fact, return the physical register to be freed. Which is again, like you still do a 2 register renaming, but just in place. Okay. We call this an R10K architecture, which is another modification to the B6 architecture. The only modification is right now we make it more centralized, one big register file. Only the value, only the tags and the controls are in the reservation station and ROB, right? I will jump all of this, and well, this is just exactly the same example. I will not, again, completely go through it, but just to show you the difference. Right now, reservation station, there is no values at all. It's only the tags. ROB, there is only the tags. And then in my register file, I have the 2 values, and then I maintain a map table. What is this map table? It simply tells me, instead of what? In B6, what did we keep here? The ROB entry, right? Why did I need to do this? Because the ROB was the one that is going to copy the value from the ROB into the register file. Right now, I no longer have my value in the ROB. I don't write values into ROB because we said we only maintain the tag. So I don't need to have the ROB entry here. What did we have in Tomasulu? The reservation station number. Why? Because the reservation station was the one that is holding the last value that is going to be written to the register file. Again, reservation station don't hold any value now. What do I keep instead is that mapping from the actual architecture, from the logical architecture name of the register in the instruction into the physical mapping to the particular register in the register file, right? Say, for example, F0 is mapped to physical register 1, F2 is mapped to physical register 2, etc., etc., right? So you basically do the actual, instead of maintaining a separate copy and you say, I have a register renaming, in the reality, this is a closer implementation to the register naming example we had at the beginning before Tomasulu, right? Because there is the assembly register names, there is the physical registers in the register file, and then I do the mapping. How do I do the mapping? With the free list, right? Okay, that's the only difference that exists here. Everything else is just the same. When you start executing, just to show you one example, when I start executing for the load, I need to allocate, well, I need to read R1, so I need to see where R1 is mapped. Assume initially R1 is mapped to BR4, and then simply, and then simply F0 is going to be written. Assume originally F0 was allocated to physical register 1. Right now, every time you write to a register, you have to give it a new name, right? That's really the essence rule of register naming. Remember when we had our example, every time an instruction writes to a register, it must write to another physical register name. Why? To avoid write after write and write after read problems, right? So this is why we maintain T old and T new. The old mapping of F0 was BR1, which means any instruction before the load that was going to write or read from F0 is going to be using BR1. While the result of the load is going to be written to physical register 5. And in my mapping, I'm updating F0 to be physical register 5 and removing physical register 5 from the map list. Good. And then here for the multiplication, now the multiplication needs F0. Well, what value or what tag that it needs to read? In the reality, if you look into the FP1 here, the multiplication needs the result of the load, which means F0 is in reality going to be BR5, right? Right. So the multiplication is going to read the physical register 5, which is going to hold the result of the load. And then for the multiplication itself is going to write into physical register 6. Originally it was 3. Multiplication is writing into it, so I'm updating F4 and then removing BR6 from the free list. Same thing would happen for the store. The store needs F4. In that case, it's going to read BR6, which is simply is going to be written by the multiplication, right? So this is applying true register renaming with the free list on top of the B6 architecture, because we removed all these data copies around and we kept one big physical register. Good. Everything else is just, again, the same. You maintain all the rules, you retire in order, you store in the issue where it's read after write. So no much difference. I just want to show you when do I have a free one of those lists. Let's say, for example, at cycle 5, I'm going to retire. I'm going to retire the load, right? Because it's complete at 4. So at cycle 5, I'm basically releasing. You see here that we have cleared the tag, and I'm releasing BR. I guess this free list is not really updated, but if you think about it, is that true? I cannot free that list yet until all instructions are using it are done. So here, you go back. This is going to write to BR5. Who is going to read it? This was needed by the multiplication. So the multiplication here. Why this one is free?
This is cycle 5.
Yeah, but the multiplication is taking 3 cycles, right? Okay, so the multiplication is busy at 5. Once the result is ready, simply the tag is done. And then free the reservation by applying T on it. Oh, because I don't maintain the actual value. Oh, but this one has to remain busy because the multiplication is not done yet. That's I don't understand. execute. Oh, yeah, okay. So in that case, given that I maintain all the results in my register file, physical register file, I in fact free the execution unit in the cycle that I basically finish execution. But in reality, there is a mistake here that I have to update because the floating point, the multiplication, is going to be done at 8. So I cannot really free it at 5. That's interesting. So I have to wait because it executes at 5. This is assuming that the floating will take only one cycle. It's supposed to take 3 cycles based on the assumption, right? Okay, anyway, so I guess that the main idea is more related to, again, the renaming. So I would stop here. Is there anything remaining to discuss? Yeah, this overall, okay. So what we are going to do in the tutorial is I just give you that big summary there between the B6 and R10K, and then solve a couple of other examples for out further execution. Okay, so see you at 12:30.